I would like to talk about another type of emerging memories. That is the Redox-based non-volatile memory devices, which are also called ReRAM devices. My co-authors are Vikas Rana, Stefan Menzel, and Eike Lin, and that's the entire group, and you'll find our co-workers among here, so a picture of Vikas is still missing. This is our funding sources, which are institutional but also industry. And that's the outline. I would like to give a brief motivation and introduction. Then I would like to step into the non-linearity of the kinetics of the switching process. I will say a few words about scaling, array considerations, so beyond cell consideration, then a few words about neuromorphic computing. Okay, now what's the motivation? Oh, by the way, here again, the title line is completely missing.
Oh, we got to fix that again.
Okay, it says motivation, the computer challenge. Yeah, that's the title line. And as you all know, the computers get better and better. They are coming closer and closer to what we can do. So some years ago, 1997, computer was winning against the world champion in chess. Then we have learned that computer can generate.
The video for a second.
Please go on. Can generate jokes, artificial jokes, where we can laugh about. Then they have been able to get proofs, new proofs for mathematical theorems, which we did not come up with. And 2 years ago, the computer was winning the world final in Jeopardy, which perhaps some of you know, or perhaps all of you know. And now if we compare, then still it's better to know where are the differences. Differences are in energy efficiency. So this machine which was winning the Jeopardy game is the Watson computer of IBM, and here are the parameters. So it is 2.3 megawatt. And we have heard similar things in the morning already. The human brain is working on 25 watts. So there is still many orders of magnitude in between, and that's of course for us in this room. For other people it may be scary, but for us it's a motivation, because there's no real reason why not technical systems may move much closer to this performance. And that is driving us. And in the framework of this talk, I would like to talk about alternative devices and alternative architectures based on these devices. So devices, non-volatile switches. We just heard a nice talk about STT-MRAM. Here it's just a different brand. Something which is better than NAND flash, high speed, high endurance, and high scalability. So what I'm going to talk about is a redox-based resistive switching elements, ReRAM, or sometimes also called memoristive elements. So it's made out of mixed ionic electronic conductor, which is squeezed between two metal electrodes, typically different metal electrodes. And the processes which happen in here lead to a change in resistance, which is non-volatile. That's the entire story. It has many flavors. Some of the flavors I will step into. Architectures, what you can think of is you can think of having something in between the hard disks and the DRAM, SRAM. So the storage class memory, and especially the storage class memory M, which has certain specifications, cannot be occupied by NAND flash. Furthermore, you can think about new computer architectures, so Boolean computer architectures beyond von Neumann, the fusion of non-volatile memories and logic, because with what we have learned, interconnect charging is the major dissipation or the major sink of where the energy is going. So the fusion of non-volatile memory and logic, crossbar FPGA type logic, that would be feasible with these ReRAMs, and beyond that we can think about neuromorphic computational concepts based on artificial synapses. Okay, the two types I would like to talk about of these RERAM are valency change mechanism. So both types are bipolar switching. The VCM, the valence change memory or mechanism is based on transition metal oxides. Within these oxides, you build up an electronically conducting filament due to a change in the valence, and then there's a little gap, a few nanometers only left towards the active electrode, which is typically tinitride or platinum in research, and you drag in and out ions, typically oxygen vacancies, but also cation interstitials. And by doing this, you change the valency of the transition metal oxide in this region, and you make it more or less electronically conducting. That's a typical loop which you can draw. And the electrochemical metallization mechanism is a bit different. You have an electrochemically active metal electrode on one side, copper or silver, and this releases in electrochemical oxidation the cations which diffuse or drift through this system, nucleate by electrochemical reduction, and build this filament. Okay, ECM and VCM. Just an example that you can switch also with quite low currents, and that's of course related to the energy. 1 microamp, that's a cell which we have built by Ti oxide. So with 1 microamp current compliance, you can really do the switching quite reliably. And if you want to compete, you must know where you are standing and where you are better than the competition. So if your competition is NAND flash, you know the endurance of NAND flash is limited. RERAM can go at least up to 10 to the 7, up to 10 to 12, it has been shown. Resistance ratio typically has to be more than 10 in order to keep periphery down. Scalability, I will come to this. It's smaller than 22 nanometers. It's also possible to have 3D stacking, and that's very important to compete to a NAND flash. Write voltage is between 1 and 5 volts. Flash needs 15 volts, so it's much better than flash in this respect. Read voltage, 1/10 of this. Write speed, typically much less than 100 nanoseconds, has been shown to be less than 1 nanosecond. Flash is more than 10 microseconds, so it's much better than flash in this respect as well. Retention in all cases is 10 years. If you take these four parameters here, then you see that the switching kinetics obviously must show a nonlinearity, which is more than 15 or 16 orders of magnitude, a very strong nonlinearity. The systems show this, or many systems show this, but we need to understand why and what's the background in order to optimize and control this. What's the future of flash? Future of flash from the ITRS, as you can see, it's not much happening. So it's a little bit scaling down further, but not much. The only thing which happens, and which is of course a strong driving force, it's going 3D. So from one layer to many layers. Of course, that's the power, and any other major memory technology has to cope with this. Okay, let's come to the nonlinear switching kinetics. If you look for the switching, we've got one of our cells, fast switching within few nanoseconds. You look at the voltage which you apply and the current which is following. Then, of course, the right energy which you dissipate is this integral of the current and the voltage. And that's the reason why you have to look into the kinetics. So again, here's these 15 or 16 orders of magnitude in the kinetics, in the orders of magnitude of the nonlinearity. Here we've got the time on the log scale. Here the voltage on the linear scale. So you want to write at a certain voltage, for example, 30 nanoseconds, and in let's say 0.3 seconds, you want to keep the system up to 10 years. So 16 orders of magnitude. Here's one example that you can tune with going from 1.5 volts to 5 volts. You can change the switching time from 100 seconds to 100 nanoseconds. So 9 orders of magnitude for a bit more than half a decade. Okay, what's the background? If you look into the physics, then there are a certain range of processes which can deliver this nonlinearity, and it's important to find out what is really giving the nonlinearity for a specific case. So one point is the electron transfer reaction over the interface, the electrolyte-electrode interface. Here we've got the overpotential, and you see it's exponentially depending on the overpotential. Here is the temperature going in, and here we've got such an asymmetry parameter. In addition, the ion transport, typically it's ohmic, it's linear. But if you have high enough fields, then it becomes nonlinear. You see that's also an exponential term, and if you have fields more than half a megavolt per centimeter, 1 megavolt per centimeter, then it's really shooting up. Nucleation probability, especially for the ECM type, is highly depending on the overpotential and, of course, the phase formation for this filament. All this can be nonlinear. And if you want to look into what physical parameters would deliver this nonlinearity which you need, here we've got this nonlinearity again. Here we've got the switching time. Here we've got the retention time. And within 1 order of magnitude, you would like to bridge this. So if you look for the electron transfer reaction, you find out you need a certain asymmetry parameter, 0.1, which is quite extreme already, in order to be roughly able to bridge this gap. The ionic transport, you need very thin gaps in order to have high enough fields in order to come up with these 15 orders of magnitude. Nucleation is, on the other hand, very, very steep, so this easily delivers high enough nonlinearity. And of course, I'll come to this. This is field acceleration. There are similar boundary conditions for temperature acceleration. So we did that for ECM type, such an analysis for a silver iodide platinum cell. So silver iodide is a silver ion conductor, quite well known. We did that in the experimental study over 12 orders of magnitude in time. So here is the time, the switching time. Yeah, you see here 10 to the 9, so nanoseconds to kiloseconds. And the dots are our experimental data for different temperatures. And these are statistical dots, as you can imagine. So many cells have been measured for every dot. And it's a very unique behavior which you find. And you can find that there are 3 regimes, 1, 2, 3 regimes. And the lines are simulations. So how did we fit that? How did we simulate this? What is the physical background? Now, we were able to put these laws, which I've just shown to you, into our simulation, and we were looking for different critical parameters which were changing the slopes and the curvature. For example, the number of critical nuclei. By changing the number of critical nuclei for the nucleation step, you can easily tune this. You can change the exchange current density. You can see its influence, and that's a nice thing about simulation. You can do things which you cannot do in experiment because you can separate things. Nucleation time constant and the hopping factor for the ionic transport, pre-hopping factor. And by doing so,
in this case, you're creating a short circuit between the silver and the platinum, and the short circuit consists of silver.
Yes, exactly. Mm-hmm. Sometimes it's only a tunneling current. Pardon?
It's a liquid cell or a solid state?
Oh, it's solid state, of course. So that's the result of the simulation. So regime number 1. Regime number 1 is nucleation controlled. Then we have electron transfer controlled, and at very high fields we have electron transfer controlled, including ionic hopping. Now we come to the temperature acceleration. So temperature acceleration, of course, by the processes which I've shown to you, which are all somehow temperature activated. So if you have, for example, and this, let's say, and you get a Joule heating in these filaments, and therefore local temperature increase, and you need a certain activation energy in order to bridge this gap, to get this nonlinearity. So it's 1.4 to 1.5 eV, otherwise you would not get that. So here we've got a VCM cell, titanium dioxide, or that's a strontium titanate cell. We made a FEM simulation of the temperature in fields, and we have put in all material data. All material data put in. And
remind us what VCM stands for?
VCM is this what is also called bipolar oxide resistive switches. Valence change mechanism, change in valency of the cations in the oxide, giving rise to the conductivity. Take 1 minute off. Okay. But I explained the acronym. Here we've got for these VCM cells, think of titanium dioxide cells, this strong linearity. The dots are the experimental data, and the lines are the simulation. And if you take into account field acceleration and temperature acceleration, you need just one fitting parameter in order to fit these dots. And you see the temperature in this filament can go up quite high. And this fully explains the nonlinearity. Now the scaling. We come to the scaling very briefly. For VCM types, we have shown some years ago already that you can scale down to something like 2 nanometers. You can switch a dot which is just 2 nanometer in size. ECM cells, the Aono group, Aono-san and his people have shown also some years ago already that you can get quantum conductance steps which are caused by single atoms. If you have such a chain, then you can show if you just take such an artificial chain of metal ions, for example, or metal atoms, and you move one out of the way, it's not sufficient. You need at least 2 metal atoms in order to get a sufficient R-off to R-on ratio. If you look now for the scaling and the kinetics, then the interesting part is that if you, for example, look for the ECM and we put in our these data into our simulation, with the decreasing feature size, so against this error, with the decreasing feature size, the nonlinearity increases. Here again, yeah, it gets better. And the same is true for the VCM type. So we used our simulation, of course, also to go down to 5 nanometer cells, and we could show, here we've got this nonlinearity. If you go from 100 nanometer feature size down to 5 nanometer feature size, it's scaled laterally and vertically, then things improve. That's nice. Okay, array consideration. Of course, you have to look not only for the energy which you use for one single cell, but you have to charge up the lines, the bit lines and the word lines. Here you have got this extrapolation. Here the bit line capacitance, bit line resistance, sense voltage, the drive voltage, operation voltage. And if you look now for different types of arrays, then you have, for example, 1T, 1R, the traditional array, but also different other arrays here, for example, the complementary resistive switches, which has the benefit that it does not compute, a non-addressed cell would not compute any power, no current, and you have the different other selectors. And now you have to, you can consider how much energy is needed for the switching compared to the cell operations. Here we've got the read time, read energy in order to have this bit line with the cell which we want to operate. And of course we have to charge up also the word line, so we have to add these two energies in order to see how much energy is consumed just by the empty array. And this is true for NAND as well, by the way. And so if you go down with the feature size, and the ReRAM can go down in feature size much better than NAND flash, then you see how strongly you can get down with your read energy. And of course the same is true for the write energy, and as well you have to charge this up as well. So if you look at just for a cell, for example, having 64 atoms charged or moved, then you have something like 10 attojoule. That's extremely small. But then you have to take into account the array. Then with the array, you end up with something like 40 femtojoule. Read energy is something like 5 femtojoule. And these are, so now I have to stop. Anyways, these are the last slides. Towards neuromorphic computing, if you look, and we have heard a few words about associative memories already, if you look for this type of memories, and the non-volatile resistive RAMs are extremely suited for this. The ReRAM, but also STT-MRAM is well suited. So, for example, if you look for what is used today, the SRAM, the 110 transistor SRAM cell can be replaced by a 5 transistor 2R, so non-volatile R cell, and you can show that this reduction already gives you improvement of 70 to 80% or more in energy consumption, and you can go further to associative networks which are based on these complementary resistive switches. Here with a capacitive readout, so a non-destructive readout, and by this you can do a beautiful pattern recognition just based on this concept, extremely energy efficient. Here we've got a summary of what we want to achieve. So if you have the human brain, sorry, there's something missing on the other side, then it consumes 25 watts. If you want to completely simulate it, you probably need 1 gigawatt to 1 terawatt. This we don't know yet. There are different numbers. Here's the energy consumption of a synapse, software simulation, and here these orders of magnitude can be gained by neuromorphic computing by resistive switching memories. Okay, conclusions. Perhaps briefly. Strong competition for ReRAM is still from 3D NAND, so NAND going 3D. Trade-off between the energy efficiency and retention. The physics must be understood in order to resolve this issue. Variability has to be worked on. These are challenges, but prospects are quite bright. Technologically, all these materials are very compatible to CMOS interface. Ultimately, high scaling potential has been shown, and there are functions much beyond the pure memory. And if you are interested in more, then you are welcome to read some chapters of this book. Please take care that you get the new edition, which is of last year, not the edition which is 10 years old. And I would like to thank you.
Maybe one question? You are monopolizing.
Okay. I'm trying to think of how this could be used for the other parts of today's meeting. And that is that if you are plating when the electrodes are the same, copper to copper, in principle, your voltage could be extremely low. Yeah, and we're going to hear about some other people speaking about very low voltage devices.
Okay.
So it seems like this could be a low voltage switch too.
Absolutely. It is. The ECM cells are very low voltage cells.
How low were they? Well, we want to go well below a volt.
For switching, for writing, it's even 0.3 volts.
0.3 volts, okay.
Reading is much lower, millivolts.